Hello. In the previous two episodes, we talked about the Hohenberg-Kohn theorem, which provides an existence proof for the energy functional and uh, formulates a variational principle for the energy functional. And we talked about the exchange correlation hole and the Kohn-Sham equations, which provide a prescription for solving the many electron problem, including electron correlation, at a cost comparable to Hartree-Fock by solving a set of one particle equations, namely the Kohn-Sham equations. But we haven't talked about what form the energy functional should take and how one can go about improving the energy functionals. So actually, long before the Hohenberg-Kohn theorems, in fact as far back as 1927, Thomas and Fermi came up with a kinetic energy functional starting with from a particle in a box model. And in this functional, the contribution to the kinetic energy at any point is approximately proportional to the 5/3 power of the electron density at that point. Thus, the Thomas Fermi kinetic energy functional is given by some constant times rho of r times integral of rho of r to the power 5/3 d tau. This Thomas Fermi kinetic energy functional gives the kinetic energy at any point r in terms of the energy of a uniform electron gas with the local density rho of r. So if we consider a molecule like this, the kinetic energy at this point is given by the kinetic energy of a particle in a small box at that point, and that is Ck times rho of r1 to the power 5/3. Similarly, the kinetic energy at this point is given by Ck times rho of r4 to the power 5/3, where which is the kinetic energy of a particle in a small box at that point. Okay. Similarly, Dirac proposed an approximate exchange energy functional, wherein the contribution of the exchange energy at any point is approximately proportional to the 4/3 power of the electron density at that point. The Thomas Fermi kinetic energy functional and Dirac's exchange energy functional are examples of what we call local density functionals, whose contributions to the energy at any point are functionals of the electron density at that point. Okay. Such functionals are reasonable when the electron density is slowly varying from point to point, but that is not the case when we are dealing with atoms and molecules, because the electron density varies quite sharply, particularly when we are close to the nucleus. It was John Perdue who came up with the catchy term Jacob's ladder of exchange correlation approximations for the systematic way of improving density functional approximations. The name derives from the verse in the Bible where Jacob is said to have dreamt of a ladder reaching all the way up to heaven. In our case, the heaven is the exact Hohenberg-Kohn density functional, okay, which let me remind you, nobody knows. Okay. In the lowest rung of Jacob's ladder, we have local density approximations where the contribution to the energy at any point depends only upon the local density at that point. In the next rung of Jacob's ladder, we have the generalized gradient approximations where the density at any where the contribution to the energy at any point depends not only upon the local density but also upon the gradient of the density at that point. In the next rung, the meta GGA functionals, the contribution to the energy depends not only upon the local density and the gradient of the density, but also upon the second derivative of the density or the kinetic energy contribution at that point. In the next rung of Jacob's ladder, we have functionals which include the exact Hartree-Fock exchange, and in the top rung we have functionals which include unoccupied orbitals. So local density approximation or LDA functionals have this general form, that is, the exchange correlation functional depends only upon the local density rho of r. The examples are the Thomas Fermi kinetic energy and the Dirac exchange functionals that we have already seen. A modification of this is the local spin density approximation, where the exchange correlation functional depends only upon the local spin densities, that is, the density of upspin electrons and the density of downspin electrons. The advantage of this is that it describes magnetic systems better than LDA. Given its simplicity, the local spin density approximation performs remarkably well for many atoms, molecules, and solids, and it has been widely used by solid-state physicists. For example, LSDA gives accurate geometries and charge densities for most systems. Binding energies obtained with LSDA are often better than 1 electron volt. Calculated vibrational frequencies are often accurate to within 10 to 20%, and in general, LSDA results are much better than Hartree-Fock. This unreasonable effectiveness of the local spin density approximation, in spite of the fact that the electron density distribution in an atom or molecule is quite far from that of a uniform electron gas, can be attributed to various exact properties of its exchange correlation hole, such as the sum rule. But there are serious problems with LSDA that render it of limited value to chemists. For example, negative ions are unbound in LSDA. The fluorine molecule is overbound by 100%. Carbon dioxide is overbound by as much as 84 kilocalories per mole. LSDA predicts wrong dissociation limits for many molecules, incorrect ground states for many atoms, and is inadequate for thermochemistry. For all these reasons, LSDA did not find favor with chemists. That brings us then to the generalized gradient approximation or GGA functionals, where the exchange correlation functional depends upon the density rho of r and its gradient del rho of r, or its spin density equivalent, which can be written in this form. Examples include the Becquet 1988 functional, the Perdue 1986 functional, Li, Yang and Parr's functional, Perdue, Birkin and Zerhoff's functional, PBE. But while the LDA exchange correlation energy functional obeys the sum rule, the GGA exchange correlation hole does not satisfy the sum rule. The next rung in Jacob's ladder is occupied by the meta-GGA functionals, where the exchange correlation energy functional depends upon the density rho of r, its gradient del rho of r, and the second derivative or Laplacian of the density del square rho of r, or equivalently on the kinetic energy. Thus, the meta-GGA functionals have this general form that they depend upon rho, del rho, and the kinetic energy. Examples include the Becquet 1998 functional and the TPSS functional, or Tau, Perdue, Staroverov and Sciarra functional. Well, you might ask, why should we bother to devise approximate functionals for the exchange energy when we know the exact exchange energy from Hartree-Fock theory? Unfortunately, adding the exact Hartree-Fock exchange to an approximate correlation functional gives worse results than local spin density approximation, due to cancellation of errors between the exchange and correlation components of the energy in LSDA. Axel Becke's fix for this quandary was to mix in half of the GGA exchange and half of the exact Hartree-Fock exchange. This is an example of what we call hybrid functionals that mix in some proportion of the exact Hartree-Fock exchange. Now, of course, this opened up the floor to a whole zoo of density functionals. You could mix in 40% of GGA exchange and 60% of Hartree-Fock exchange, or 70% of GGA exchange and 30% of Hartree-Fock exchange. You could generate a lot of papers and keep churning out such papers. Okay, for example, you have the B3PW91 functional, which mixes in some proportion, that is A0, of the exact Hartree-Fock exchange with some proportion AX of the Becke 1988 exchange and the Purdue-Wang 1991 correlation functional. The popular B3LYP functional is defined with a similar formula, except that now you mix in the Li, Yang and Parr's correlation functional instead of the Purdue-Wang correlation functional. Well, as long as we are parametrizing, why stop with just 3 parameters? Some recently developed functionals, such as the Minnesota functionals, are heavily parameterized, in some cases involving more than 50 parameters. With little or no empiricism, the accuracy of the density tends to increase as we ascend Jacob's ladder of density functional approximations, that is from LDA to GGA to meta-GGA to hybrids. Until 2000, both energies and electron densities became more accurate upon ascending successive rungs of Jacob's ladder. But since then, energies have continued to improve while the electron densities have become less accurate. So that leads us to ask, are we getting the right answers for the right reasons? If you look at the history of density functionals and the error in the electron density, we see that recent density functionals have improved the energies but not always concurrently improving the electron densities. So if we look at historical trends in the errors for the density, its derivatives and the energy, we see that the energy as given by the black bars has continuously improved over time, whereas the electron density given by the red bars and its gradient and the Laplacian have gotten worse in recent times. Thus, functionals constructed with little or no empiricism may produce more accurate electron densities than highly empirical ones. So, how do we get the right results for the right reasons? Well, the Hohenberg-Kohn variation theorem guarantees that the exact functional should give the exact energy for the exact electron density, but not for the wrong electron density. As we have seen, functionals constructed with little or no empiricism produce more accurate electron densities than highly empirical ones. Increasing the number of parameters does not guarantee systematic improvement towards higher accuracy. That is, the Jacob's ladder framework is no longer valid. Accuracy does not necessarily improve upon ascending the ladder. Heavily parameterized functionals may not always be reliable for density-dependent properties such as dipole moments, charge distributions, and spin densities. Of course, this is not unique to density functionals, but is the same for any parameterized or machine-learned model. The training set used to develop the model and train the parameters of the model should be developed and should be trained on similar molecules and similar properties as the model is going to be used on. In the fifth rung of Jacob's ladder, we have energy functionals which depend upon virtual orbitals. Some researchers consider this to be not truly in the spirit of density functional theory. In range-separated functionals, we use different functionals for different distance ranges. So one functional for the short range and another function for the long range interactions. For example, to deal with dispersion, we have Stefan Grimm's empirical dispersion correction, or D3 correction, or the Bekke-Johnson dispersion. So what is dispersion energy? Well, standard density functional theory is wrong for two reasons. One is that excitations to virtual orbitals are not included. And secondly, when you are dealing with intermolecular interactions, the density is actually non-zero for large distance between the fragments. Dispersion is a time-independent phenomenon. The London part of the dispersion energy is a long-range correlation effect, which goes as r to the power minus 6. It continuously becomes part of the normal correlation energy for short and medium distances, and it is not included in standard cone-sham density functional theory. The short and medium range part, however, is included in cone-sham density functional theory to different degrees. Dispersion is often considered weak, but can sometimes be quite sizable. For example, if you're looking at the Coulomb interaction between 2 point charges separated by 10 Bohrs or half a nanometer, that's approximately 60 kilocalories per mole. But the dispersion interaction between two fragments or molecules each containing about 100 atoms of hydrogen, carbon, nitrogen and oxygen is also of the same order of magnitude, around 60 kilocalories per mole. So this is the Stefan Grimm's D3 dispersion correction, which you see the leading term has this r to the power 1 upon r to the power 6th dependence. Here we see how inclusion of Stefan Grimm's D3 dispersion correction improves the binding energy of a fullerene dimer. Here these are the energies curves obtained with the TPSS functional and the BLYP functional without including dispersion, and here we see the curves including the D3 dispersion correction, and the experimental binding energy is around here. Thus far, we have considered atoms, molecules, and molecular complexes. For periodic solids, however, as I mentioned in a previous episode, it is more convenient to use a plane wave basis instead of an atom-centered basis, and to use periodic boundary conditions. For this, we consider a box and repeat it in all three dimensions. In the augmented plane wave approach, the potential is spherically symmetric inside a sphere around each ion. The solutions to this are spherical harmonics. Then we match the all-electron wave function inside and outside at the boundary of the sphere. In the projector augmented wave approach, we use smooth functions plus an added function only inside the sphere. Bloch's theorem states that the solution to the Schrödinger equation in a periodic potential can be expressed as plane waves e to the power ik dot r modulated by periodic functions u and k of r. This u and k of r is a periodic function with the same periodicity as the crystal. N is the band index, k is the wave vector associated with electrons, which is related to the crystal momentum h cross k. The charge density is periodic, but the wave function can vary in phase in going from r to r plus t, where t is a translation vector. The potential has the form V of r equals sigma I V of r minus Ri, where the sum is over all the cells and over all the atoms in each cell. Ri is the position of the atom in the ith cell. Then we can expand the density as sigma g rho g e to the power ig dot r, where g is the reciprocal lattice vector, and the potential as sigma g vg e to the power ig dot r. Then from Bloch's theorem, u and k equals 1 upon root omega sigma g cg e to the power ig dot r, and phi nk equals 1 upon root omega sigma g Cg e to the power I g plus k dot r, where omega is the volume of the cell and Cg are the expansion coefficients. In practice, only those plane waves are included that satisfy h cross squared by 2 me modulus of g plus k whole squared less than a certain energy cutoff. This is a schematic diagram showing a one-dimensional periodic potential in a crystal. The positions of the nuclei or ions are shown here. The potential in the core regions are spherically symmetric. The core regions remain atom-like and localized around each site. The potential in the internuclear region will depend upon the crystal structure. The potential at the surface of the crystal goes to 0. DFT calculations on periodic solids often use pseudopotentials. That is, we consider the potential from the nucleus and the core electrons to be frozen, since the core electrons are localized and generally not much affected in going from atoms to molecules to solids. We consider explicitly only the valence electrons. These are the electrons that are responsible for bonding and most properties. And these valence electrons are considered to be moving under the field of the ions. They will be attracted and scattered by the positive ion cores. If the scattering properties of the electrons can be as well reproduced by a pseudopotential as by treating all the electrons, then we have a good description of the material without explicitly considering the core electrons. Relativistic pseudopotentials are often used for heavy metals, and these include special relativistic effects which can be considerable for the inner core electrons of heavy metals. The density functional theory we have discussed so far applies to ground stationary states. Remember, that's what the original Hohenberg-Kohn theorem applied to ground states. But consider the time-dependent electronic Schrodinger equation. H operating on psi of Rnt equals I del del t of psi of Rnt, where the time-dependent Hamiltonian is given in terms of the time-dependent external potential, and this can include interactions with an electromagnetic radiation field. This leads to the time-dependent Schrodinger equation shown here. For many years, there was no density functional theory for excited states or for time-dependent systems. But in 1984, Runge and Gross showed that there is a one-to-one mapping between the external time-dependent potential and the time-dependent density of the system. The potential is defined up to an additive purely time-dependent function, and such functions change only the phase of the wave function and leave the density invariant. Since V of Rnt is the time-dependent potential and ρ of Rnt is the time-dependent density, this includes the response of the molecular system to electromagnetic fields, including light radiation, which can induce an electronic excitation to an excited state. Since the energy is not conserved in a time-dependent system, the starting point for TDDFT is the variational principle for the quantum mechanical action, which is the time integral of the expectation value of I del del t minus h. This leads to the time-dependent Kohn-Sham equations minus half del I squared plus Vks of Rint, that is the effective time-dependent Kohn-Sham potential, operating on phi k of Rnt, the time-dependent Kohn-Sham orbitals, equals I del del t of phi k of Rnt, where the effective time-dependent Kohn-Sham potential is given by this expression, and the time-dependent density is the sum of the densities of all the occupied time-dependent orbitals, and the time-dependent exchange correlation potential Vxc is given by the functional derivative of the exchange correlation action with respect to the time-dependent density. And this Sxc includes all non-trivial many-body parts of the action. We shall stop here for today.